In this video, I wanted to hit some of the highlights from section 2.3, which discusses different ways to prove that lines are parallel. So you may remember in section 2.1, we had many statements that began with the hypothesis if two lines are parallel, and then we filled in with different conclusions. So for example, we had if two lines are parallel, then the corresponding angles are congruent. That was a postulate. We had some theorems that we proved. If two parallel lines are cut by a transversal, then the alternate interior angles are congruent, and so forth. So we did mention a transversal, but in all of those cases, we assumed that the two main lines were parallel. In this section, 2.3, we're dealing with what types of hypotheses would be sufficient to prove that two lines are parallel. So you just want to keep track of this because this time we are trying to prove what was formerly our assumption. Okay? So we, in this section, cannot assume that the lines are parallel. That is the goal of different proofs. Okay, so here is one of the theorems in this section, and then I think if we go through the proof for this one, the other proofs you can read through from the book and try some of these on your own as well. But as long as we establish one of these proofs, then we have something to work with for all of the other ones. Alright, so this theorem states if two lines are cut by a transversal so that the corresponding angles are congruent, then these lines are parallel. So notice this is not a postulate. In the previous section 2.1, our corresponding angles one was a postulate, but this one we can actually prove. So we're starting with two lines, L and M, and I don't know if this diagram is large enough for you to see, but we have, you can follow along from the textbook if it's not. This is figure 2.16, and this is on page 97. Oh, sorry, 87. Okay, so we have lines L and M, they're cut by a transversal T, and we know that angle 1 is congruent to angle 2. So we're starting with the assumption that the two of the corresponding angles are congruent. And then we need to prove that L is parallel to M. Okay, so if we try to direct proof here, we don't have a whole lot to work with. We don't have much in the way of facts about corresponding angles. The only thing we had previously was just if the lines were parallel, then we know they're congruent. And in this case, we don't know that the lines are parallel, so we can't use that postulate. And we already know that the corresponding angles are congruent. That's our assumption. So instead, we're going to try an indirect proof or a proof by contradiction. So we're going to start by assuming that L is not parallel to M. And the complete proof is written up in your textbook, so I'm going to do more of a shorthand here and just sort of get an outline of the proof. Okay, so we start by assuming that the lines are not parallel, and then we want to try to get some sort of a contradiction. Alright, well, one of the things we know is that through a point there is always a parallel line to another line. So if we focused on the part of the diagram that has M, and then if we look at point P, which is currently where L and T intersect, okay, so let's draw T through this, and we'll skip L for now. But if L is not parallel to M, then we know that through a point not on line M, or in other words through P, we know for sure that there is a line parallel to M. So we're going to draw it in, and since in the original diagram L sort of looked like the parallel line, then when we draw this new one that's now supposed to be parallel, we kind of go at a diagonal here. So it doesn't look parallel, but this is our assumption that this new line, which we've called R, that this one is parallel to M. Okay, so we can say R is parallel to M, and then the reason for that is the parallel postulate. Okay, so that's our reason why we know that we can draw a line R parallel to M. Well, what does that mean? Well, now if we look at some facts from the previous section, right, we know that if two lines are parallel with a transversal running through them, so still transversal T, then we know a lot of information about the different angles involved. So in particular, let's pick out this angle, and we're going to call that angle 3. And this angle from the original diagram was angle 2. All right, so now we know that since R and M are parallel, that means that 2 and 3 must be congruent. Okay, and that was a theorem from the previous section. Okay. All right, so what's the problem with that? Well, if you focus on maybe this original diagram, all right, let me draw a little larger the piece of this that's the problem. All right, so here's an enlarged diagram, and what we know now for angles, we assumed that 1 and 2 were congruent. All right, so, and then we also know that 2 and 3 are congruent. All right, so since congruence has a transitive property, then since 1 is congruent to 2 and 2 is congruent to 3, then we can now assume that 1 is congruent to 3. Okay, and that's the transitive property. All right, well, what's the problem with that? Well, if you look at the diagram, intuition would kind of lead you to see that it's really not possible for 1 and 3 to be the same measure. The only way for that to happen would be if this little angle, right, sort of between R and L, and this is labeled as 4. Okay, the only way for 1 and 3 to be the same is if 4 is 0. And we know from the protractor postulate that 4 can't be equal to 0 degrees, and that's our contradiction. All right, so the rest of this is just getting to that point. How do we prove that? Okay, so we need some sort of a statement that talks about the fact that the measure of angle 4 would have to be 0 degrees. So you can see if we're starting to work with degrees, we need to start talking about the measures of angles and not the congruent fact. So the next place we want to head is probably the angle addition postulate. All right, so we know next that from the diagram that angle, let's say the measure of angle 3 plus the measure of angle 4 equals the measure of angle 1. And again, this is sort of just an outline, so if we were actually going to do a really formal proof here, we should probably label these angles maybe with some letters and things like that. All right, but we'll go with this for now. So we know 3 plus 4 equals 1. And then since we just said that 1 and 3 were congruent, so we know that the measure of angle 1 equals the measure of angle 3. All right, so we can substitute one of those in place of the other in our previous equation. So we could do something like measure of angle 1 plus measure of angle 4 equals measure of angle 1. Okay, so substituting 1 for 3. And then we could subtract from both sides, and we would get that the measure of angle 4 equals 0 degrees. Okay, and then we could state that there's a contradiction by a contradiction of the protractor postulate. Okay, angles have to have a positive number of degrees. All right, so then we've proved a contradiction. So if you trace the statements all the way back up, the only one that was unjustified was the fact that L and M were not parallel. Right, so since we've proved that that statement leads to a contradiction, then we know that that statement can't be true, so its negation would have to be true. So therefore we can say, to finish it off, that L is parallel to M. All right, so that's the harder proof. Now if you wanted to go on and prove some of the other theorems in this section, we could use this theorem now as a justification in our proof. So I didn't include it in this video, but for example, theorem 2.3.2, states if two lines are cut by a transversal so that the alternate interior angles are congruent, then these lines are parallel. Right, so here are two lines, we'll go with L and M again, and a transversal T, and let's assume that alternate interior angles, we'll call them 1 and 2, are congruent. So 1 is congruent to 2. Then if we wanted to prove that the lines are parallel, well, we already have one theorem that we just proved. If we could show that corresponding angles are congruent, then we could just state theorem 2.3.1 as our reason. Right? So you could go from, this is a really short proof, this one's included in the textbook, but you could just look at angle 3 here. That's a vertical 1, 2, 1. And you could say that angle 3 is congruent to angle 1 since they're vertical angles. And we know vertical angles are congruent. And then since we have the transitive property, then we would know that 2 is now congruent to 3. And then you would just state that those are corresponding angles. So then by theorem 2.3.1, since corresponding angles are congruent, then that proves that L is parallel to M. So basically we did the hard proof, and then all of the rest of these are just based on that one, and you're just using the angles that you're given and sort of working towards the fact that that corresponding angles are congruent. And now once you've progressed past theorem 2.3.2, now you can feel free to use this one. So now another strategy is to show that either the corresponding angles are congruent or that alternate interior angles are congruent. And both of those would be proof that the lines are parallel. There is some discussion at the bottom of page 87 and top of page 88 about how to tell which lines are parallel in a more complicated drawing with more than just the two lines and a transversal. Sometimes you'll see a figure like this one, other times we may get into shapes, so maybe like a trapezoid or a parallelogram, and we want to work with some angles there where maybe not all of the pieces of these lines are shown. So how do we tell which lines are the ones that are parallel? So let's start with an example. Let's say 1 and 3 are congruent. Well, your book suggestion is to think about the lines that are necessary to form those angles. So you almost want to just trace the angles and then just keep drawing those two lines. Okay, so we have this line forms the base of 1 and 3, and then we also need these two lines. And then notice that line D really has nothing to do with those two angles. All right, so then if 1 and 3 are congruent, right, then think about what types of angles those are. So if we're looking for two parallel lines, well, you can see like it's not going to be line C parallel to D if we're not even considering D. So it's got to be that A and B are the ones that that are parallel, and then we just need to check and make sure that one of the conditions is met, right? So far we want either corresponding angles to be congruent or alternate interior angles. And in this case, 1 and 3 are corresponding, so we would know that A and B are parallel by theorem 2.3.1. What about if 3 and 8 are congruent? If 3 and 8 are congruent, so trace out angles 3 and 8, and then just sketch and extend the rest of the lines that make those angles. And here you can see that the relevant lines are C, D, and B, and that A really doesn't have anything to do with those two angles. Okay, so compared to the two, it looks like C and D are going to be the ones that we hope are parallel. So we just need to figure out what types of angles 3 and 8 are. Those are alternate exterior ones, and we didn't go through the proof, but theorem 2.3.3 says that if alternate exterior angles are congruent, then the lines are parallel. And then finally, what about 1 and 5 if those are congruent? So let's trace those out. So here's 1, and and here's 5. Okay, so all 4 lines are traced. All right, well, one option is that we have too much information, so maybe A and B are parallel and C and D, or maybe we don't actually have enough information. So try to think about the relationship between 1 and 5, and sometimes it's helpful to put numbers to this. So let's say 1 and 5 are maybe like 100 degrees. I'm going to erase this. We had all of these traced anyway. So let's say these are 100. Okay, well, what else do we know? Well, the vertical ones to those would also be 100. Okay, vertical ones are congruent regardless of whether or not the lines are parallel. And then we know that linear pairs are congruent, so like 5 and 6 are on a line, so that would have to be 80. 7 would have to be 80. 2 is 80, and this unlabeled one is 80. All right, but what we're looking for is a pair of lines that we could show that are parallel. Now, for instance, like if you look at angles 1 and 5, the 2 in question, those are not corresponding angles because they would have to be on top of a pair of parallel lines, right? Hopefully parallel, and on the same side of the same transversal. So if we wanted to say that maybe C and D were parallel, and if we wanted to use corresponding angles to show that, then we would need either A or B to be the transversal, but 1 and 5 are on opposite, one's on A and one's on B, so we can't approach it that way. What if we try to show that A and B are parallel, and maybe C or D is the transversal? Well, same problem, 1 and 5 are not on the same, they're not both on C or both on D. So we can't go about it that way. So basically what we would have to know something about angles 3 or 4, and then we could use sort of this pair of angles to show A and B are parallel, or we could use these 2 pairs to show that C and D are parallel. So when you have like diagonal sort of information like this, there is not enough information to show that any of these lines are parallel. Okay, so from this diagram, if 1 and 5 are congruent, we can't show that any lines are parallel. All right, and then there are also some examples in this section and some exercises just asking you to find sufficient conditions to show that the lines are parallel. So it's not a proof, but we are determining what measures the angles would have to be to make these lines parallel. So we're given that the measure of angle 1 in this diagram is 7x, and that 2 is 5x, and then we want to find the value of x so that L and M would have to be parallel. All right, so we have a relationship between angles 1 and 2, and compared to L and M, those would be consecutive interior angles. All right, so you would need to think through what condition needs to exist for those consecutive interior ones to make the lines parallel. And these are let's see, theorem 2.3.4. If 2 lines are cut by a transversal so that the interior angles on the same side of the transversal, so that's consecutive interior, are supplementary, then these lines are parallel. So if angles 1 and 2 were supplementary, that would be enough to show that L and M are parallel. Okay, so then we can translate this into an equation. So what we want is for the measures of angle 1 and angle 2 to add up to 180 degrees. And then we can use substitution to substitute 7x and 5x in place of those measures. And then we are all set to solve for x. So we would have 12x equals 180, and then just divide both sides and get, let's see, and then you would get x equals 15. Right? So looking back at the find statement, we weren't actually asked to find the measures of angle 1 and 2, we just needed x. So check that statement, make sure they didn't ask you to continue and find the angles, and if not, then we are done. We just needed to find the value of x. Alright, that's all I have for comments on section 2.3. Read through this section, make sure you see all of the different conditions that would be sufficient to show that lines are parallel, and then try some of the exercises, maybe some of the ones that were unassigned, just to check and make sure you understand these different concepts.